Okay, let's have the final talk of today's session. And so it will be given by Huanchen Bao from the National University of Singapore, and the title is Symmetric Pairs in Symmetric Spaces. Let's welcome the speaker.
Thanks, Bart, for the introduction, and also thanks for the invitation. It's a pleasure to speak here. And as Bart mentioned at the beginning this afternoon, basically all the three talks about symmetric pairs and some is the generalization. And you've heard two talks about quantization, and this talk is mainly about actually the classical setting. I'm actually going to use the quantum version to obtain results on the classical setting of symmetric pairs and symmetric space. So that's basically the goal. And I will start with just a group case, and algebraic group and quantum groups. I'll explain the connection. And then basically sort of imitate everything in chapter 1 to chapter 2 on symmetric pairs and also symmetric spaces and quantum symmetric pairs. I will try to put more emphasis on the first part, since basically that's a familiar theory, and the second part I will try to give you the idea and omitting technicality. Okay. Let's start. And I have two parts. Chevalley group scheme and diagonal symmetric spaces. Technically, both should be Chevalley group scheme, but I just don't want to use the same name. So you'll know what I mean. Okay, and so first, Chevalley group scheme. And the setting we start with is just the connected reductive group, and over any algebraic closed field. For convenience, we can just take complex numbers. I want to fix the Borel and the torus, and x be the character, y be the cofactor. And I just set a simple root. And if you want an example, typically this example I'll give you basically focus on rank 1 example. We have SO2C, and the Borel center choice just upper triangular, and the torus just diagonal matrices. Okay. And Chevalley in 1955, that's a long time ago, constructed the integral model of this Chevalley group scheme, and basically just a group scheme over integer, such that when you take in geometric fiber, this just becomes the reductive group. And his construction actually depends on choice of dominant weight. And constant later give the constant Z4 on the enveloping algebra, which is basically a more universal construction of this Chevalley group scheme. But Constant's construction doesn't really have a proof. I'll mention somewhere the thing is not trivial, so somewhere you need a proof. And the proof actually appears in the Lucic paper, not that sort of in the history, it's 2009. He gave a construction of the Chevalley group scheme, basically proving some missing part in constant construction using canonical basis. And that's something I will recall. Okay. And basically, as an example, the Chevalley group scheme in the SO2 case, just a prime spectrum of this ring, Z of the entries of matrices, x11, x12, subject to the condition determines 1. Okay. And we will construct this in a more general setting. And equivalently, by Unita lemma, we can also think of this as functor points from the category rings to the category groups. So for each ring R, the R point of SO2 is just invertible matrices with entries in R, which is basically same as the homomorphism from this ring to my ring R. Okay, that's the equivalent way. We'll also talk about the second construction as well. And so, just as I mentioned at the first page, basically it doesn't matter which algebraic closed field you take. And the idea behind it is once we have a connected reductive group, we can obtain real data. The one give you weight lattice, root lattice, and the pair in between them, etc. It's the same data. So that's why the particular characteristic doesn't really matter. And from there, we already see that once we have the real data, we can construct the universal enveloping algebra, let's say over complex numbers, which is just algebra modular relations. The only depends on is really depends on real data. And then we have the quantization, by Jinfeng and Huanchen Bao, we have the quantum group. You can think of it just as a quantization of the enveloping algebra, or sort of more straightforward, just algebra with generators as relations, only depends on the real data. And one thing I want to emphasize is here, the second one, the overlapping algebra is going to be co-commutative, but the quantization is actually not co-commutative. And this is actually why all the interesting happen, like nothing invariant, for example. Okay, so we want this phenomenon. And just example, in the GO2 case, and the quantum group basically just generated by EF and the Cartan part Kn, n for all the integers. And we have very small amount of relation. The multiplication between caton just adding up the indices, and the conjugation of E just Q to the 2n. Notice that, this is actually important. And then we have a commutative relation between E and F, while obtaining the caton part, and similar thing for K conjugation with F. But we also have, in rank 1, we also have reductive group at the PGL2. And we can also have a root beta attached to this and define the quantum group. It's almost the same, except that now the generator, we have a conjugation Q to the N. Looks like the same, but in the first case, you're never getting odd power. So that's something I want to keep track of, because if you're working over, only working over the algebra, this is minor, but if you work on groups, this is actually a major difference. Okay, and just an overview, why quantum group is important. I think somehow this appeared earlier in the discussion. The quantization usually makes things easier, not to make it harder. And the situation is using quantum group, basically we can recover all the classical situation just by specialization. And intuitively, if you have a quantum group, let's say I sort of secretly assuming the first line is defined over a field rational function. You can have a Q equal to 0, you obtain the enveloping algebra. But this is only like a heuristic, because we don't really have a field morphism for CQ to C. There's no such morphism. If you want to do this kind of specialization, what you have to do is define what is integral 4. And here is really the quantum version of integral 4. Integer becomes ZQQ inverse. And then we have a ring homomorphism for A to integers. At the specialization, we have cosine Z4. And then we can embed to the enveloping algebra. Even though intuitively the first line is what everyone is saying, but to make that precise takes a lot of effort. And this also appears earlier in the discussion, in the question about roots of unity. And once you have integral 4, you can also specialize Q to roots of unity. You're getting UQ at roots of unity. And here you can again further specialize Q to be 1. Okay? Or you need to do a little bit more. You can do Q is 1 and also go to character P. And then what you're getting here is algebra distributions. Okay? And let me emphasize, since here the bottom line, I mean character P is the Lie algebra and the enveloping algebra are slightly different thing. So here what you're getting here is algebra distribution, not the enveloping algebra. This one you need to consider Diconchini cats. Okay? And the sort of everything behind it, making all the specialization works nice, because we have a nice theory of canonical basis. At the specialization becomes again a basis downstairs. Okay. All right. So now I'll talk about how to construct this Chevalley group scheme using quantum groups. And so start with the modified form of the quantum group. You should think of this just as a completion. What we want to do is replace the identity with summation of weight space or idempotent. And basically the idea is when you consider representation of quantum groups, you only want to consider those semi-simple and cut off. You don't want to consider this weird thing. So effectively it's the same when you consider representation. And then over there we have the Lucis canonical basis, basically a very nice basis. That's the short summary. I'll mention where this come up. And one particular thing, just let you see why this is nice. Suppose we have action map to highest weight module tensor with lowest weight module. A basis under this action map, a basis go to basis or 0. And in general, you have a quotient map, whatever thing. You don't really have a basis to basis this kind of phenomenon. This is basically saying that this is a very nice basis. That's sort of why it's called a canonical basis. And inside there, we have this integral 4, or more precisely, this quantum version of the integral 4. Again, A is just ZQQ inverse. And this is just generated by this divided powers, E to the N, F to the N. And if you define this as algebra, it's non-trivial. We have a reasonable basis. As a matter of fact, this is actually a sub-algebra spanned by the basis. Okay, this is just one thing to say the basis is a good basis. And now, once we have this kind of integral 4 as a quantum version of this cosine Z4, we can do specialization. Because now this ring is ZQQ inverse. It's very easy to construct a ring homomorphism from this ring to any arbitrary ring. You can just mapping Z naturally to this ring R and mapping QQ inverse to arbitrary invertible element. Okay, imagine you start with A to be a field. In general, there's no morphism from one field to other things. It's very rare. Okay, and particular example already show up. We can consider just consider go to field of fraction, doing nothing. and then we have enveloping algebra over the field fraction. Oh, sorry, the quantum group over the field fraction. We can also specialize Q to 1. We're getting constant Z4. You can also specialize ZQQ inverse to character P, and then you're getting this algebra of distributions. Okay, so now I'm just consider the classical setting, and I want to consider ring homomorphism from A to Z mapping just Q to 1. And then because this quantum version we have a basis, so now we also have a basis as specialization. That's the basis is nice. And now I want to define a subspace inside the dual. And note that basically if you're taking the complete dual is too large, it's infinite rank. It's just like we generally don't want to taking a dual of infinite dimensional space. We want to put some kind of restriction. So the restriction I'm putting here is I want to take the subspace to be spanned by the dual canonical basis. And this basis is constructed by quantization. So even though at the end, the only thing we care is in the classical case, but the construction of a basis, you have to use quantization. By dual basis, that just means it's sort of a B is 1, B dual is 1 at B and 0 everywhere else. Okay, and this is the result I mentioned in Lustig 2009. And this ring over Z is a commutative half algebra. And it's algebra basically because UZ is half algebra. It's half algebra basically because that one is algebra. So dual of everything. And what is non-trivial is this is actually integral domain. This is a much harder thing to do. Okay, this is the integral domain. And if you're taking the prime spectrum of this commutative ring, you're getting precisely Chevalley group scheme. If you want to, you can take this as definition, since I didn't give you a definition. And at the end, if you're taking geometric fiber, taking base change to XP where algebraic closed, this is precisely the coordinate ring of the algebraic group. Okay? Or in other words, if you're taking the group scheme, you're taking the fiber in XP and precisely or any characteristic, you're getting the reductive group we start with the same data. Okay? So that's the coordinate ring I promised. So now, basically because the construction is by dual, we can also constructing this by functor point. And this R point of this group scheme is basically ring homomorphism for OZ to R, which basically taking double dual back is actually inside the completion of this enveloping algebra base change to R. And the morphism, because we define everything by dual basis, it's just a naive map you write down. In some sense, this is precisely just the group-like elements in the universal enveloping algebra. Any questions so far? Remark, this is where sort of the cousins construction come in. And we start with algebra basically only on the complete dual because the multiplication, co-multiplication on this OZ is coming from multiplication and co-multiplication of this enveloping algebra or quantum group. So in other words, technically the multiplication only works in the first line. If you restrict to sub-algebra, it's not clear the multiplication preserves the sub-algebra or subspace. That's the non-trivial thing comes in. Okay, that's really the part that sort of Cosset didn't prove. The multiplication closed on subspace. Okay, and this is actually using some very fancy property of a canonical basis. You have some vanishing condition. That's basically. Wait. Everything is dot. Yeah. Everything is with dot. Yes. No, for everything, if you define this, if quantum group, pardon? Q and Q square. No. They're different. Yes, you have different. Yes. The issue is here. The root data you're choosing X. You're only choosing X in the weight lattice. So PGO and SO2 are different. Lie algebra is the same thing, but depends on what kind of theory you want for Lie algebra. You could keep track, but since everything is linear, it doesn't matter. Exactly. But if you keep track of the data, you actually keep track of isotopy class. And also here, yeah, I forgot to mention. Here, this is integral domain, basically corresponding to the fact what we started the group is connected. Okay? later you'll see we're getting non-integral domain because we're getting something disconnected. Any other question? All right. All right, so now 1.2. And this is basically, as I mentioned, I want to call this diagonal symmetric space. K is algebraically closed. And basically, what I want to study the symmetric space in this particular example is still the group. We know the group is a symmetric space just by considering this as G times G over the diagonal embedding. Okay, and the multiplication, the isomorphism is just a multiplication morphism. And this is a symmetric space. And we want to consider the module structure of a GK times GK on the coordinate ring. And this is the multiplicity phrase. And in the sense that any BK times the Borel eigenspace is always one-dimensional. And if in character 0, everything is much simpler. We don't even care about Borel eigenspace. We actually have a decomposition into V dual lambda times V dual, this is the longest element, just height weight times height weight. This is irreducible as the product group. Okay? The group is the product group. But situation becomes dramatically different in character P. It's not semi-simple anymore. We cannot really talk about multiplicity phrase as irreducible appearing only once. The only thing we can talk about is the B eigenspace. So that's the blue part is for. That's the more general definition of multiplicity phrase in positive characteristic. But in positive characteristic, we don't really have the decomposition like this, but we have something close. That is, we have a good filtration. In the sense that this coordinate ring, we have a filtration parameterized by dominant weight, such that if you're taking consecutive subquotient, we're precisely getting the Weyl module we have. Okay? Let me mention that here in character P, this is just a dual Weyl module. It's not reducible anymore. Pardon? Next page, I will show you how. Yes, but next page, I will show you how you can prove this using quantum group. Okay? Yes, everything classical, as I mentioned. Everything's classical, no quantum. As Ivan's question?
I do my best to slow down a little bit, but without my success.
Oh, sorry, thank you. You should have pointed that out. Okay, let me slow down. Yes. Yeah. So now we recall earlier I mentioned the Chevalley group scheme. We can construct this using quantum group. And because we can identify the group with the symmetric space, you can think of this Chevalley group scheme also as a sort of a scheme theoretical construction for the symmetric space, even though it's making things complicated, not necessary. All right? And so next, basically, I want to just mention a little bit. We can also understand the good filtration using quantum group, not just the computer ring. Okay. Okay. And this is just the previous page. Let me recall a little bit. I'm going to use the same thing. And U is, again, the modified quantum group. And we have the canonical basis. And we have the A form. Again, it's crucial working everything over Z QQ inverse, not over field, because I want to specialize the different characteristic. And then we have this commutative algebra we defined when we specialize Q is 1 and everything like that. Okay? Okay. And so now inside here, what you want to consider analog to this good filtration is this for the cell ideal. And if you're familiar with the Cauchy-Looser cell in the Hecke algebra, this is precisely the analog in the quantum group setting. And the way to define this is you can actually define ideal inside the modified quantum group. The definition is in blue. If you don't like it, you can just ignore. Basically, we can have defined ideal parameterized by dominant weight. The way to define this is by vanishing condition. Okay, we want to consider elements that does not vanish only when this highest weight is large enough. Okay, and you can check this ideal, and then this basically gives a filtration of this modified form. And what miraculous, this is my star here, is this is not just a normal ideal, this is a cell ideal in the sense that the basis we have is compatible. In the sense that we consider intersectional basis with the ideal, we have a basis of the ideal. That's the non-trivial thing comes in. That's why I call it cell ideal instead of just ideal. And now just by
Clarifying question, it's not a question. So what we are doing, we are reproving Peter White theorem
exactly
using canonical base. And
exactly.
This is the only way, right? You need
Exactly. That's potential.
Another proof and very new proof, right? Of the same old stuff about either way, right?
Exactly.
It goes characteristic 0 and characteristic not there, right?
Exactly. Exactly. That's what I'm trying to show here. But technically, maybe harder since you need a harder thing on canonical basis. Yeah, but just a new proof. Yeah. Okay. Yeah. And so now, since this ideal is a cell ideal, we have a basis. So now we have a quotient. Those become non-zero. It will be a basis on the quotient. So basically, that's my a slightly abused notation. B minus the basis element, what remaining, will be a basis on the quotient. So technically, we take image. Okay, but since the basis is multiple basis, I'm sort of hiding this. Or if you want to, just we have a shorted that sequence that is not just a shorted that sequence, it's a base shorted that sequence in the sense that we have a basis in the middle, restriction here become basis, whatever mapping here become non-zero is the basis here. Okay. And next page is everything explaining why we care about the basis, why this is good. And everything can be defined over A. That's my repeating the first line. And now we have this below on the quotient. This just becomes V lambda times V negative W0 lambda. We just need to do a little bit computation over A. Okay? And so now this is split if you go to field in character 0 because representation of a quantum group basically the same as representation of a looping algebra, at least in CQ. So you basically have the same theory, but again, you need to do the actual work to do this over integers. So now, if you want to obtain anything in character P or in classical theory, we want the Q goes to 1 and go to field, characters P or characters 0. Yes. Yes, exactly. Not always C. So now, if we go to base change from A to K, what I just mean is mapping Q to 1. Hello? Oh, yes. Wonderful. Thank you very much. So I think people can understand this page better since we look at this longer now. And so now, suppose I have a ring homomorphism for A to K. Here, I only consider Q to 1, even though you don't have to. I only consider Q to 1 and then Z mapping to whatever Z will go to this unique way. And then this base change the claim as this is also exact. And the reason precisely because this is a base. We're mapping basis to basis. There's no weird definition. For example, you think of a non-example. Suppose I have this to be even integer lies inside here, or equivalently, this is multiplication by 2 map. Yes. Yeah. What I want to say is always exact. That's my claim. Split, I just want to say when over C, it's easy. Exactly. Okay. And so this is exact. What I want to say, the non-example here is suppose we have Z to Z multiplication by 2, and here if you go to characteristic 2, you'll see this is not exact anymore. Okay, because once you go to character 2, this becomes 0 map. Okay, so really this exactness of this line and above line really is something nice about this being based morphism. We're mapping basis to basis, so then we can do base change to any characteristic. Okay, so now another definition, basically reformulating what we did with this commutative ring OA. Now I'm not writing Z, I'm writing over OA, but hopefully we're all familiar what I mean here. Basically the dual space. And so now instead of just taking this as the subspace spanned by dual canonical bases, I can just take this as a union. But once we have writing this as a union, automatically you're going to have a filtration. just by taking the dual of each strata. Okay. And so now by earlier result, as I mentioned, the coordinate ring of OK, the OK is the coordinate ring of G, but now naturally we have a filtration. And then by taking this filtration, dualizing everything in the previous page, this is precisely just a good filtration. This is just dualizing, this is just dualizing this line. Okay. Okay, not only we get a good filtration, each sort of each component we have in here actually naturally have a basis by construction. Okay. Any question? Yes. Yes. Any questions so far? Okay. So now next part is about symmetric space, symmetric pairs.
Some remarkable functions on Chevalley group of canonical basis. The key question. So we have canonical basis, right? Then there are some remarkable, according to what you described, some remarkable functions on anyway FG. Chevalley. Do you have some interpretation of geometry or whatever interpretation?
Yes, I think what do you mean geometric interpretation? I mean,
in what sense? See it from Chevalley theory. You remember Chevalley theory is X post impact elements basically, right? Do you have some kind of connection with this one parametric subgroup? Anyway, the foundation.
One parameter subgroup.
But do you have some interpretation inside Chevalley theory or canonical basis? Canonical basis can't be defined unless you introduce Q. Q is a must. But can you do some play with rules of unity? I don't know what, right? Just to
I'm not sure. I mean, what do you mean by special? There are cross algebra theory relevant to that. Maybe that's one. You can do that. And another thing, you can also define like a total positivity. That's again cross algebra coming. That's one thing. And you also have like a categorification, many other things. I don't really have any particular answer. Yeah, but it's a good. Yes, all makes sense. Yeah, it all makes sense. Yeah. Any other question? I'm just worried if I go to next page, someone will have a question. All right. So now, basically, what I'm trying to do, and everything before now is like a classical theory, and everything I'm trying to do here is just generalizing that from the group to only the symmetric space. So two parts: symmetric subgroup scheme, the generalization of Chevalley group scheme, and symmetric space. And now I want my field to be algebraically closed, but I don't want the characters 2. Anything in character 2 for a symmetric space when involution is going to be a little bit strange. And so now I want to have an involution of my algebraic group. And this is actually classified by Springer. This is independent of K, as long as K is not a character 2. And for character 0, it's the same as the real reductive group. That's even earlier by Cartan. But since I'm talking about arbitrary characteristic, I'm just putting Springer there. And I want to pick a Borel subgroup inside this group here, such that theta will move this further away. And this was briefly mentioned in Andrew's talk about static diagram. Basically, the position between the two Borel is just the lines element times the lines element of the black dot. That's the opposite as far as possible. And this involution will be called a split or quasi-split if this is the opposite Borel. Okay, that's just the geometrically how everything works. You can translate this just by computing everything out using Satake diagram as well. And the fixed point I'm denoting by K, this will be just a symmetric subgroup. Okay, my K is always a group K. There's no K matrix. I want to mention a little bit on this. And let me mention this is generally not connected. And the first example is already, if you take in PGL2, the fixed point will just not be connected anymore. Okay, if it's simply connected, the fixed point will always be connected. And the choice of my Borel, basically what I want to K times B this to be the unique open orbit on the flat variety. So in other words, I want them to be transversal to each other. And this general doesn't really matter, but the situation is when you do quantization to quantum group, you don't have the flexibility to change the Borel. You have to fix the Borel. So that's where we have to fix the Borel to start with. Okay. And this involution will induce an involution on the weight on the simple root. Okay. I'm not going to a little bit detail, but this is how you draw the Satake diagram. And this also gives the decomposition of a simple root to be a white one and a black one. That's where you draw the Satake diagram. So classically, that's sort of the Satake diagram is 4. You want to have a classification of this involution. So you work out certain data there. And this also introduces the involution of the weight lattice and the co-weight lattice. And then we can create the quotient and the fixed point. So let me mention a little bit. Again, this is subtle. And this quotient in general is not a lattice, but very often we call this a lattice. This is not a lattice, it's also relevant to the isogeny class. If you're taking PGL or taking GL, this sometimes will be lattice, sometimes won't be. This corresponds to the orbit structure. Okay, but we just call this lattice, let's say. And just like the situation with this reductive group, we know this is classified by raw data. And this kind of a G with involution can also be classified using just I raw data. What I mean is all the data above. A raw data with involution satisfies certain properties. Okay, you can just reverse engineering basically. And this just the data you need to define what is the quantum symmetric pair. Instead of a classically defined quantum group using only raw data. Okay? All right. So example, right, I have example. I forgot. Yeah, so basically in the SO2 case, what do we have? We have an involution SO2C to SO2C. We can consider this a rotation of matrices. That's one involution. But you can also define this in a different way. Basically, they correspond to the same thing. They're conjugate to each other. You can also define this just by this matrices. And in SO2 case, it doesn't matter. Both of them you can define over integer or arbitrary field. However, if you're looking closely, you'll see the second one, this definition, what you need, really you need to conjugate with negative roots of unity. So you have to have this I exist. Exactly. But what I want to say is I want to define over Z, even though it looks fine, it actually matters. If you want to go to more higher rank, this really matter. But I don't want to show too complicated example. Exactly. Over C, it doesn't matter. Okay. So yes, as I mentioned, as Ivan mentioned, over C, it doesn't matter. There's no difference. Both of them are torus. All right. So now with this data, we can introduce what is quantum symmetric pair or what is I quantum group. I think the name I quantum group, I is really for invariant involution. Because it's not exactly fixed point, we don't want to call it a fixed point. That's why we call it UI. That's the name coming from. And this subalgebra generated by particular elements of generators. I just give you some example. It's something like this. And also there has been early question on the parameter. This perceived I is basically you have a choice of parameter. I'm hiding there. Okay. And this subalgebra is going to be co-ideal subalgebra. We've seen this already. It's not half subalgebra. It's very rare to have half subalgebra inside quantum group. Okay, so generally this is the best you can hope for. And this, at least in this formulation, I'm taking is originally for finite type. Sort of defining this generator relation is by Lester. But the origin really coming from the reflection equation, as already mentioned multiple times. I think that's even her motivation to study everything in general. Okay, yeah, that's before this even. And in joint work with Wei Chang, we developed the theory with canonical basis, which I'll mention how to use this in a minute. But basically, that leads to many other reflection equation, the K matrix, as Andre mentioned, and also Twisty-Yang many development following. Okay, so now this page is basically copy paste what I did earlier, because basically I want to justify the whole theory is parallel. Instead of having a modified quantum group, I just want to have a modified form of this I quantum group. Again, almost the same, I'm replacing identity with idempotence. And then we have the I canonical basis on this modified form as analog to Lustig. But unfortunately, there's not a very good crystal theory. There's some progress by Watanabe. I'll mention some of them actually play an important role.
Can I ask you, it's not satisfactory because there's no combinatorial map really, because One basis element goes to sum of basis elements and things like this, right?
Exactly.
Okay.
So if you want to have asymptotic theory, I would expect this to be yes. If you want something analog to Cauchy-Euler operator, I would say no. If you compare with the Hecke algebra side, the Cauchy-Lutz cell of type A basically is nice. If you go outside type A, the cell theory Cauchy-Lutz cell will become a mess. That's basically what you're expecting here. Exactly. Yeah. Asymptotic theory, yes. Cauchy-Euler operator with nice capital-rays, probably no. Yeah. And so now with almost parallel to what the Lucic did, we can define the A sub algebra generated by this we call I divided power. You should think of this just analog of divided power, or a subspace spanned by the spaces, which miraculously is algebra. It's closed under multiplication. So now basically similar to what we did earlier. Once we have this algebra.
The same question. So when Q goes to 0, distance exists, right? But you cannot leave that canonically, right? What is missing?
A different question. I think it depends on what you want by crystal. Crystal to me is you have a nice Cauchy-Euler operator with good capital rays. That exists. That is fine. Lifting is fine. The thing is that you don't have a good capital rays. There's no good analog of Cauchy-Euler operator moving basis to basis. Q to 0, what I want to say is asymptotic theory. Yeah. Yeah, that should exist. Yeah. That also exists. That does not exist is combinatorics. Combinatorics. Yeah, combinatorics does not exist. Lifting or asymptotic theory both are fine. This is just analog of the Lucic J ring, or in terms of this Briefman Cauchy-Lutz work with Schwartz space analog. That should exist. Yeah. Pardon? That's a good question. I'm not talking about that. Maybe I'll mention this. Can I hold on the question? Yeah. So now once I have basis, I can do base change. Basically the same thing as I did. And again, if you want to do base change, you have to have integral form. If you're working over field, there's no flexibility anymore. That's why over integer is important. So now basically copy paste what Lucic did. We have this algebra base change to Z just by kicking Q to be 1. But because I'm in the classical case now, co-ideal actually becomes half algebra because I'm working in the sub-algebra of enveloping algebra. There's no braid anymore. Again, we define the subspace spanned by the dual canonical basis, entirely analog to Lucic. And that's the theorem, the first theorem with my student. This is actually commutative half algebra. And we have a surjection just by restriction from the dual of Lucic quantum group. And what this precisely say that the prime spectrum of this define a closed subgroup scheme of the Chevalley group scheme. And that's what we call symmetric subgroup scheme. Okay? That's the definition. A prime spectrum of a ring.
We use symmetric space, not subgroup.
I'm getting there. So now, not yet. And because I want to claim this is actually symmetric subgroup scheme, because in the group scheme case, smoothness or geometric smoothness is basically equivalent to being reduced. This ring is reduced for any domain, as long as characteristic is not 2. And the geometric fiber of this, for any algebraic closed field K, is precisely the symmetric subgroup we start with. And I want to emphasize in this is functorial. If you want to fix just over C or fix a field, you don't need the whole fancy theory. Okay, I want to emphasize the global theory working over integers. And basically a consequence of item 2 reformulation, this OI of K is precisely the coordinate ring. And now, as I mentioned earlier, this is commutative half algebra. If you recall earlier, I mentioned a Lucic version, this is the integral domain because it's connected. Here, I didn't mention this is the integral domain because K may not be connected. This may not be integral domain. Okay, and now basically once we have this scheme theoretical construction of K, our original motivation is actually want to study the orbits of flat variety. This is relevant to representation of a real group. And so now once we have a scheme theoretical definition of the K, we can also define K orbits. And basically by general theory, we know this K orbits can be defined as open subscheme once we invert in 2. And back to Andrew's question, and the de Maistre analog is basically what we know is Schubert variety is always defined over integers. And here, we don't really know what's a good analog of this sort of algebraically or quantization of de Maistre. That's sort of preventing us. We don't know how to precisely show that any orbit closure is defined over Z adding 1/2. By general theory, we know we only need to throw away finite many primes, but we don't know 2 is the only thing to throw away. That's basically we don't have a satisfactory theory with Dimosou. And we expect this to be equal.
You mean even within Chevalley theory, without quantum?
Yeah, because the situation is I'm simplifying a little bit because the situation we know super variety is divided over integers. That's sort of the consequence of Dimosou module has a canonical basis defined over integer. We don't know that here. That's precise issue.
We all of us, right? We don't know, right?
I don't know at least.
It is not known.
I think it's not known. Yes. Okay. And this is our original motivation to study the whole thing because now we can just have because now we have a scheme over Z to parameterizing everything. We can go from special fiber to generic fiber. And here we have a characters P method, like Frobenius splitting everything. So you can use geometric method to prove normality or vanishing cohomology. That's our original motivation of everything. And a little bit of remark. And the difficulty of the whole thing is, again, to show this modification is actually closed on the subspace. Just like Lustig, if you define a subspace, you're taking dual, it may not be closed on the modification. That's the fancy property of the basis. That's something we use Watanabe result on this crystal. And also the surjective morphism to show that this is actually closed subgroup is actually compatibility between I-canonical basis and the canonical basis. Pardon? I'm hiding here, but basically, let me explain Lustig setting. What in Lustig setting, what you have is you have a highest weight and the lowest weight. You can map into a smaller highest weight, smaller lowest weight. You have a basis, go to basis or 0. Here, there's the analog of that, precisely. It's a vanishing condition. Yeah. And we expect this group scheme is a fixed point of scheme. Basically, it's saying that this is a parameterizing, this is a scheme, and you have a family of a scheme, basically. We don't know how to show this. In particular, I'll show you an example. We know in character 2, things will be strange. I'll show you an example in a minute. So that's something we also don't know. And finally, our original motivation really study the K-orbit closure on the flag variety. And we can show normality of closure and cohomological vanishing of ample line bundle. And that's our original motivation of everything. Example, early example we have. And we want the involution dependent over integer. So basically, we're taking the evolution I'm describing earlier, rotating matrices. And now you can check the fixed point group scheme. Yes. What we want for Frobenius splitting is, first, if you just want to consider Frobenius splitting of flag variety, that is, you can do this geometrically. What we're interested in is compatible splitting with K-orbit closure. So then you can consider restriction of line bundle here to the K-orbit closure. You can show if there's a vanishing H1. That's what it shows. And also the closure if normal or not. That's what it shows. There are because in general for super variety everything holds. For K-orbit closure, we know there are orbit closure that is not normal, not with rational singularity. We also have H1 does not vanish for ample line bundle. So things are bad. So basically, we can obtain some, very sort of, we actually have some kind of algorithm to show everything already. Yeah. In general, it's not true, but we can show certain orbits are normal. That was the previous unknown. Yeah. And of course, because the scheme theoretical construction, this implies character 0 by semi-continuity. Yeah. How am I doing on time? It's okay. And so now just back to the example I was running, SO2. We have SO2Z, and the involution I'm taking just on the functor points, rotating matrices, because I want to define everything over integers. And then the fixed point subscheme, the functor points, basically we're taking matrices such that A, B, B, A with the determinant condition. So it's very simple. And then you'll see the symmetric subgroup scheme, writing the commutative ring, is just this ring modulo determinant, and with extra condition here. If you simplify this, this is just Z of AB quotient A squared minus B squared equal to 1. Very simple. Now you already see trouble. This is not going to be reduced scheme in character 2 because we have a nilpotent element. In character 2, this relation becomes A plus B plus 1 equal to Z. Okay? Because we're in character 2, this is the same as a squared plus b squared plus 1 equal to 0. Okay? Yeah, we have a nilpotent element. So things are a bit strange. Yeah. What I want to say, things are strange. Even though we can define the scheme over Z, F2 points, generally very strange. And you can also define the finite group in this version. I haven't thought about anything like that yet. Okay, potentially you have Suzuki group or Reese group, something around this. I have 12 minutes, right? Good. No, I'm good. I'm good.
7 minutes plus 5 minutes questions.
Okay, I'm good.
But you provided 2 forms. For the second form, maybe it will be okay. Right?
Pardon?
You provided 2 equivalent over
Yes.
the form.
Yeah.
For the second, it will be
That's a good question. In this case, if you consider the other one, it happened to be torus. Everything worked out nicely. But generally, no. That's basically because the one SO2. In general, it's not okay. Yeah, exactly. Yeah, this is because the SO2 is too special. Exactly. I think you got me there. Yes. In this case, this is actually the harder way because the SO2, the other one gives you torus. Everything is actually work out better. So now, instead of symmetric subgroups, I want to talk about symmetric space. Again, in the group case, the two things merge together. But for general, those are two different things. And by Steinberg, I actually forgot which year. And we know the fixed point is always reductive, may or may not be connected. And because it's reductive, the geometric quotient is always affine, which just means the coordinate ring is precisely just k-invariant functions. And we also know this is spherical, which one way or another way to say that, we can know B has open orbit, because our choice of Borel, this Borel has open orbit, or equivalently, this coordinate ring is multiplicity free. Again, what I mean is the B eigenspace is always one-dimensional. And in character 0, for symmetric space, we know we have this decomposition. I think this will go to hexagon, maybe. And we know since the representation of G is completely reducible, so we can decompose the coordinate ring just to direct sum. And you can actually work out, and this actually, if you want to work out nicely, you do need our theory. I'm describing how to define the weight lattice. It's actually in terms of this quotient lattice I'm describing there. Okay, I'm not going into detail there. There's a very concrete way using our new method. But now the question is, this is a very classical question. What happened in capital P? Okay, you can guess the result, but that's basically the claim. So I'm giving you a theorem first, and then go to the construction. So theorem, this is Olin posted earlier this year, and we define affine Z scheme G over K. Note that I'm writing as G over K without subscript K. Okay, I'm indicating that this is not really open algebraic closed field. This is basically defined as a prime spectrum, again, of a commutative ring, such that if we're taking the geometric fiber, we're precisely getting the symmetric space. That's basically a Z model for the symmetric space. And again, characteristic is never 2. But our scheme is defined over Z. I don't know what happened to F2 points. That's something I'm always curious. And on the other hand, we all basically by construction or analogous to what Lucy did, this coordinate ring, or we do any base change, it has a natural dual canonical basis. Okay. And finally, just by construction, analogous to Lucy, this one has a good filtration. And this was never known before. And this is, I would think this is a very classical result in the bottom one. Okay. I will talk a little about the definition of a ring. But before moving on, any question now? And so the construction of this ring, the idea is actually not very hard. What we want to consider is a k-invariant. On the dual side, we really just want to study co-invariant. So on the dual side, we basically just want to consider the UI co-invariant of this base module. For any base module, we can define co-invariant. And if we're taking dual, that's going to be invariant. Okay, the co-invariant, very simple, just a quotient of this augmentation ideal. I'm taking right action because I want to G mark K on the right. Left action is the same thing. Okay, so now instead of doing this module, what we want is just working on this on U. On U, we can consider it's a co-invariant U over this. And that's precisely taking dual because of our early result on symmetric subgroup scheme. We identified UI and the symmetric subgroup. This will give us precisely the UI invariant, which is the coordinate ring. That's basically the idea. Okay. Modular technicality I will mention in a minute, because everything he's saying here is not exactly correct, but that's the philosophy here. Okay. And we want everything to be, yeah. So recall, this is what previous page I have. We have a base homomorphism on quantum group, and because we have a base homomorphism, when do any base change, it's going to be exact again, because basis to basis. When you do base change to positive characteristic, nothing strange happening. And so basically, we want the analog of this to guarantee that base change is good, even though it's not flat. Okay, so that's basically a big technical theory we have on basis. We have a very big commutative diagram that is both exact and based. The exactness shows that we have a good filtration, and the base basically showing that it is based on any base change. That's just analog of this theorem. Okay. Okay. I'm not going to detail, just giving you the flavor because the precise definition will take too much time. Okay. And so now basically, but just by doing this, we can recover just what Lustig did on the coordinate ring on the group. However, not exactly recover, because what we recover is really on the right-hand side. But what I showed you earlier is on the left-hand side. You have to pass over from each other by the isomorphism. And even if you try to work on Lustig setting on the right-hand side, it's still going to be hard. But for exactly, because in general, there's no such isomorphism. Yes, in the special example, we have this isomorphism. In general, we only have this picture, but not this picture. This will be easy. That's what I'll say. So you have to work on right. Yeah, that's what I'll say. Yeah. All right. All right. And so now I can just give you a definition of a ring. It's basically just consider the dual of co-invariant. Again, it's too large. We want to consider those expanded by the dual basis. And then we also have a filtration, because almost by construction, we can just consider co-invariant of those ideal Lustig original defined. And then this is spanned by the dual basis. So at the end, just by combining those two, we are going to have a union of this coordinate ring, of this commutative ring, parameterized by lambda, lambda just as dominant weight. Okay, and then doing base change with everything, we have filtration on the coordinate ring and on the coordinate ring. So note that here I'm writing definition as dominant weight, anything with I, because some of them will be equal. Because I didn't show you the computation co-invariant, some of them actually will vanish. Pardon? Oh. Okay. And finally, I want to say the first one is not exactly correct. Because the first one, there's no canonical basis, too large, we need completion. So that's all the technical difficulty comes in. Sorry. Yeah, hold on. Where am I? Yeah, this picture is not 100% correct. The first line is incorrect. We need to replace that by a projective system. That's the technical detail, but I just want to show you this picture. Okay? That's the difficulty. Yeah, I'll stop here. Thank you very much. Please.
You see, people use this. Oh, sorry. It resembles me, but just resembles the machinery, modern machinery. When you need to prove that from algebra of your kind that something is Cohen-Macaulay or something, you do quantization and then you can prove it, right?
Exactly.
It looks almost exactly like this.
Exactly.
Yeah? Through canonical basis, right?
Exactly.
Some difficult problem about Z modules of some Chevalley, whatever. Okay.
Yes, that's totally the philosophy. Without quantization, you cannot construct the basis. So even for classical question, you need quantization. Exactly.
Sometimes problems like proving something difficult that it is Cohen-Macaulay or whatever, right? Which can be proved by this technique,
Exactly.
right?
Exactly. That's the geometry.
Which examples? Some Schubert cells are nicer than they can be expected.
This one, K-orbit closure. That's something we can prove just using this method. Yeah.
Frobenius splitting is a different techniques, you know, right?
Yes, it's a different technique.
Quantization is much very interesting.
That's a different question.
Yes,
so the way to construct the Frobenius splitting, we actually need to construct the quantum version of Frobenius splitting first, and then do base change the capital P.
You need some vanishing homologies, you know, right?
Yes.
But with quantization, normally, anyway, think.
The point is the construction of the splitting using quantization. The final result is only capital P. Exactly. Yeah. Exactly. Yes, and then final geometric result has nothing to do with quantum group. The final result is only geometric.
Okay. Any more questions or comments?
So is this dual canonical basis compatible with the dual canonical basis?
It's different basis. It's different. What do you mean compatible? Like a basis to basis? On the symmetric space setting? Which page should I point at? This one, maybe. We have a subspace inside O over G. Is that the question?
So is this O of G mod K? How to say? Can be embedded into O of G? Or?
Yeah, you can embed in the O of G. This is the K invariant function.
Yes.
Hold on. Yeah, this is the basic K invariant function you can be embedding. And it's not compatible. It's different.
Okay.
Yeah, this is not going to be. This is basically a dual canonical basis. It's not going to be canonical basis. It's different. Yeah. And my student did some computation on low rank, and there are some interesting class algebra on this. We don't fully understand yet. Yeah.
Can we see the little while group here?
Pardon?
The little while group?
Little while group basically just a while group of symmetric space. So here we have lattice. Little while group is just basically a while group of this lattice. You can actually concretely compute. It's just a while group of symmetric space. That's one word definition. We can define other way. Exactly. Yeah.
Any final questions or comments? If not, let's thank Huanchen.
Okay, thank you.
And let's thank all the speakers of today for great 5 talks.